So for those who never heard about interval arithmetic, I will start by a motivating example. So let's consider this very simple problem. I want to show that if I take a polynomial of third order, then if I substitute the root of the polynomial for the variable x, I get 0. So of course I get 0, so it's not a problem. And this must work even if the multiplicity of the root is any number, for instance 30, so it's still 0, of course. But now let's try the same with the root equal to 3. And now I don't get 0, but some 4 million. So this is apparently not the correct answer. And the reason is that I use machine precision, computation in machine precision, in double precision, so some 16 digits. And this is caused by some rounding errors. And moreover, it is the question why it works with 4 and it doesn't work with 3. I'm not going to analyze this example here, but I will just say that the problem is that when I expanded the polynomial, I have high powers of 4 here and 3 here, and high powers of 4 are representable in machine precision with no problem. It's just power of 2, but high powers of 3 are not so easily representable. The number of significant digits grow with the power. So if it exceeds 16, then some rounding must occur. Okay, and what can we do in this example with the interval arithmetic? If we take this computation and we don't plug just the number 3 into the polynomial, but an interval that contains 3, then the answer is some interval, and the basic thing with the interval arithmetic is that the correct answer, the exact result, must lie in this interval. So as you can see, 0 lies in this interval. So of course that the interval arithmetic is not more precise. It doesn't tell us the correct answer, but it can tell us what's not the correct answer. What lies outside this interval is not the result for sure. Of course, it may happen that if we plug, for instance, 4 into the polynomial, then the exact result is 4 minus 3 is 1 to 30 is 1. So the interval contains the number 1, of course, but it also contains 0, so I don't know if it's root or not. But one of the things that I may do is to increase the precision from the double precision, which means about 16 digits, to 30 digits, and I get a smaller interval which still contains 1, but now it doesn't contain 0. So now I can be sure that 4 is not a root of this polynomial. So generally speaking, the interval arithmetic can never tell us what's the exact result, but it can tell us what's not the result. And now it's a question how it can be used in an application. And as I mentioned, we used it in research of differential equations, and I will explain how. So first, a short introduction, what problem we were interested in. So it's such a boundary value problem. The domain is a unit disk in a plane. We have a Dirichlet boundary conditions, and we solve this eigenvalue problem. Lambda is the spectral parameter, and this equation is some strongly nonlinear equation. The operator at the left-hand side is called P-Laplacian. It's a second-order partial differential operator, and it's a generalization of the classical Laplace operator. So if you take P equal to 2, then this is 1, and it's a classical Laplacian. If you take any P greater than 1, you get generally a strongly nonlinear operator. And the problem that we were interested in is spectral properties of this eigenvalue problem, namely how the second eigenfunction looks like, if it's radially symmetric in the disk or not. So first, let's look at the first eigenfunction. Maybe I should mention that the eigenvalue is defined like a value of lambda such that this problem admits a non-trivial, a non-zero solution, and the corresponding solution is the corresponding eigenfunction. So the first eigenfunction that corresponds to the least eigenvalue looks like this. This is for p equal to 2, and it is known that it is radially symmetric, and it doesn't change sign in the domain. And we wanted to prove that the second eigenfunction, which must change its sign, is not radially symmetric. So if we look at the second radially symmetric eigenfunction, which looks like this, now it changes the sign. We wanted to prove that this eigenfunction is not the second one, that the second one has a smallest eigenvalue than this one. It is still an open question if the nodal domains are 2 halves of the circle, or how do they look like. Okay, so how did we prove that this eigenfunction, the radially symmetric second radially symmetric eigenfunction, is not the second eigenfunction? Let's consider this initial value problem for this ordinary differential equation. And the solution of this initial value problem we call a P-Bessel function, and we denote it by J0P, because if you take P equal to 2, you get the classical Bessel J function. So it's a generalization of the Bessel function. And by some variational arguments that I will not present here because it's not the purpose of this talk, we showed that if we prove that the first 2 roots of the solution of this problem satisfy the first 2 roots, Ni1, Ni2, satisfy this inequality, that the second root is greater than 2 times the first root, then this implies that the second radially symmetric eigenfunction is not the second eigenfunction. So the second eigenfunction is not radially symmetric. And to prove this inequality, we used interval arithmetic. So let's first look at the case p equal to 2. The zeros of the classical Bessel J function are approximately this. So you can see that the second is more than twice as big as the first one. So to prove this inequality, we used three different techniques. For p equal to for p close to 1 and close to infinity, we used some asymptotic analysis. We didn't use Mathematica or computers there, but for p between 1.01 and 226, we used the interval arithmetic. And I will shortly explain how. The thing that we did was to integrate this initial value problem, but with values in intervals. So we introduced some interval-valued dynamic system, for which the exact solution of this initial value problem lies in the intervals, which are the solution of the interval-valued dynamical system. So generally, I will explain it on a general first-order initial value problem. U may be a real function or a vector-valued function. So our problem is a second-order problem, so it can be rewritten as a system of two first-order equations. First, at the right-hand side, we have a general function f, which depends on the independent variable and also on the solution. And the first thing that we need is the so-called interval extension of the function f, small f, which is a function that takes two intervals as arguments, and it produces an interval for which for any small r from the interval capital R and any u from the interval u, the value of the function small f must lie in the interval which is the image of this mapping. So this is a fundamental property of the interval extension. Of course, the interval extension is not unique. It may produce wider intervals than it's necessary, but this implication must hold. And now let's take some step h, and we start to integrate the initial value problem. It is important to know that first we must have an a priori estimate of the solution, because for a general initial value problem we cannot be sure that for a given interval 0h there is a solution at all. So we cannot do any estimate, of course. So we must have a priori estimate for the solution. I will denote it by I0. For instance, for our P-Bessel function, it is easy to show that the solution always lies between -1 and 1. I'll show it on a picture. So this is for p equal to 2. This is the classical Bessel function. So the Bessel function always lies between -1 and 1. So this can be proved easily even for the P-Bessel functions. And what we do next is that we take this a priori estimate, and we plug this interval I0 into the right-hand side for u, and the interval 0h here, and not into the small f, but into its interval extension. And we must get an interval for which the derivative of the solution on the interval 0h must lie in. So we get all possible values of the derivative in the first interval for the first step. Now, of course, u is a primitive function for its derivative. So if we take all possible values for the derivative and multiply it by all possible values of r, it's between 0 and h, and we add the initial condition, then we must get an interval such that the solution must lie in this interval on the whole interval 0h. So we get some interval I1. We can do this that if this interval is maybe wider than 0,1, so we do this. So now we know that the interval I1 is possibly smaller than the first a priori estimate, and we can repeat it as many times as we want. We can again take the interval I1, plug it into the right-hand side, and we can get an even better interval, and so on. And our experience shows that 3 iterations are, in a sense, optimal. So if we do another iteration, then the interval doesn't significantly squeeze. We get some interval for the values of the solution on the first interval 0h, and then we continue on next intervals h, 2h. In the same manner, we take again some initial condition. Now the initial condition is not just this number. It's u0 plus the step times all possible values for the derivative on the interval 0h. So with another initial condition, we can do the same, and we continue on next intervals until we cover the interval that we need. So I will show again a picture what result maybe get. So I will use the 3 iterations here. So it looks like this. The green area depicts the intervals where the solution must lie, and the curve is just computed by ND-solve. Of course, ND-solve gives a result which is precise enough, but ND-solve doesn't give any guaranteed error estimates, of course. So the green area has the advantage that it's guaranteed. The solution must lie in this area. And of course, if we take smaller steps, we get better result, smaller area. So if I change the length of the interval to 8, and I take 2000 steps, then you can see that the solution must lie in this area, and I have also intervals for the roots of the solution. You can see that the second root must be something greater than 5, approximately, and the first is lower, is less than 2.5. So if the left end for the interval for the second root is more than twice as big as the right endpoint for the interval for the first root, then we actually proved that the second root must be at least twice as big as the first root. And this can be considered as a computer-assisted proof. And we did this for any p greater than 1. Sorry, not any greater than 1, but for p between the numbers 1.01 and 226. And we proved that the inequality that we needed is satisfied, and this implies that the second eigenfunction is not radially symmetric. So that's all. Thank you for kind attention.